further, you'll understand when they're talking about things dealing with polymers in the news. And a lot of other organic chemistry that finds its way into the news, you'll be aware of. All right. It's talking about polymers. Remember, polymers are macromolecules, a huge molecule made up of repeating units called monomers. And there's two different ways of classifying polymers. One is by its chemistry, the other is by its physical properties. And I talked about addition polymers yesterday, where you have only one monomer that repeats over and over again. Things like saran wrap is an addition polymer. If I look out the window, I see a lot of cars out there, all of them have tires on, and the rubber out there is an addition polymer. So if I were to ask on a test, give an example of an addition polymer, you should be able to do that. All right. Now, the other type of chemistry is called condensation polymers. And condensation polymers are made with two or more different monomers. And generally what we're talking about is to connect them together, unlike where addition polymers are radical polymerization, which I mentioned the other day. Condensation polymers are general reactions between two functional groups. And the molecule, each monomer, usually has two of the same functional group. So that way when they connect together, each end is still another functional group that can help build on and on, like a train, connect boxcars together. And the two main functions for general reactions that are used to make condensation polymers, you already know, I'm keeping my promise, no new general reactions that will be on test. Take a carboxylic acid and alcohol, what do you get? An ester. If you take a carboxylic acid, plus an amine, what do you get? An amide. And so I don't forget. That's sort of when I go through the editing, I know which one it is, because the camera doesn't put a date on it, so this helps me. All right. So like I said, usually condensation polymers are made by making an ester or an amide. And there's some others I'll just briefly mention, like a urethane, which you'll make in, I think, 2 weeks or more. You'll be making in the lab, and it'll be a lot of fun. Actually, it's next week. All right, now, if we look at polyesters, and again, here, switches in the off position, click, will be on the test. But this is still good background for the rest of your life when you hear people talking about polyesters. My lens of my glasses are polyester. My water bottle is a polyester. Many things are polyester. And what you have here is, in this case, a dicarboxylic acid, a diol, a molecule with two hydroxyl groups. And notice here, just like on the board, you form an ester. And here I have further functional groups that I can now react with. This side more alcohol, form an ester there. This one more to diacid. And I'm going to do something I haven't done before. Let's see if I can find an example of some polyesters. I'm doing that. Most of you, like just about everybody here, is probably too young to remember. For a while there was this craze in clothing, which was awful, I thought it was, called polyester everything. You had polyester shirts, polyester pants. I had a polyester suit coat. My mother guy was in freshman year of college, and it was like wearing a rubber wetsuit. It wouldn't breathe, and it was awful. And they don't make that anymore. One of the best days of my life was when I gave that suit and pants to the Salvation Army and got rid of it. All right, let's try something. here they talk about polyesters now with cotton, which a lot of this is probably has synthetic, not pure cotton. This one's pure cotton. But a lot of yarns and things like that. Also, another polyester is this. And if you have certain stretch material, I wonder what spandex is. Let's take a quick. Do I have time? Oh, I do. And spandex is a mixture of two different polymers. One is polyester, and the other is polyurethane, which I'll talk about. And therefore, if you have things that you like a lot of the leggings that stretch, you're wearing a polymer. Well, by the way, cotton is a polymer too, but it's a natural polymer. So if I were to ask you to give an example of a polyester water bottle, and it's also a condensation polymer. Now, the other type is a polyamide. And there's a very famous polyamide that most of the women here have heard about, but under another name. How many of you have heard of nylons? And now what do they call? Pantyhose. And that's a polyamide, nylon. And originally nylon was discovered or invented, I think invented is more a better way, was in World War II because the Japanese occupied certain islands and areas in Asia and were the enemies of the United States during World War II. They cut off all supply of silk to the United States. And in wartime, what's an important use of silk? For parachutes for the paratroopers. So the government, the United States government went to, I think it was DuPont, and other companies too, and said, can you come up with something replacing silk? And the answer was nylon. How it got that name, and polyamides are used extensively now in industry and your everyday life. But here's one I'd like to talk about. This is an acid chloride. Acid chlorides react just like carboxylic acids, but much more quickly, more reactive. And here I have a diamine 2, nitrogen, hydrogen, carbon. And when you have a benzene ring in something, it makes it stiff. Cyclohexane, as you learned, you have the chair and boat. Benzene is this flat and very rigid. Well, when you react these two difunctional groups, monomers, diamine, diacid chloride, which is the same as the carboxylic acid but more reactive, you'll form an amide here, and the repeating unit is this right there. Notice the key thing, carbonyl, carbons, nitrogen with carbons and the hydrogen, amide. This has a trade name, this specific amide. It's called Kevlar. And they can make it and make it into thread or yarn, weave it. And what do they weave it into? Sheets of material. And what are those sheets used for? Bulletproof vests. I think you've all heard of Kevlar bulletproof vest, and that protects the policeman. And there's also another thing that the military used along with Kevlar. Besides having that, they also have a place to put in ceramic plates, and we call that body armor. And that protects our troops when they go to battle. Now, another one, did I talk about polyurethane yet? Yes.
Not really, but I just have a quick question about like spider silk, because I know that's like a really strong, they say it's like one of the most strongest materials.
I don't know, I haven't worked in that. But I know I've heard the same thing, but I would assume so, but I'll be honest, I haven't worked in it. But for many, many years, they've come close, but they haven't duplicated exactly what a spider can do. And what does a spider do? Mother Nature doing organic chemistry again. Like I said, she's the greatest of all organic chemists. But silk, which is what, does a spider make silk or not? I'm thinking of a silkworm. So I'm not sure what the web of a spider is. I'll tell you what, email me, I'll look it up this weekend and let you know on Monday if I can find something. That's the nice thing about having knowledge. You can look up other things and Learn. New thing. Hi, this is called an isocyanate. And did I go through this already? Okay. I think I did in the other class, that's why I'm getting confused. And this is a functional group which won't be on a test. And if I use my magic chemistry hands, what do you see there? A carbonyl. It turns out isocyanates react like carboxylic acids. If I react this with an alcohol, and I'll need a catalyst here. And usually use a tertiary amine catalyst like dimethyl cyclohexylamine. And you'll see on the next slide, I do have it on the next slide. You form a urethane. I'm missing a hydrogen there, so don't look. Look on the board, don't look there. No. And what happens is, just like in making an ester, this attached to carbonyl, carbon bonds to it. And this is called a urethane functional group. Carbonyl, oxygen with carbons, nitrogen with carbons. And this is used to make a number of things. One of the things it makes is the foam you're sitting on right now. That's called a flexible urethane foam. It's a condensation polymer because you're bringing together two different monomers. Another use for this is to make a rigid foam, and that rigid foam is used for insulation. Now, how many of you have ever seen a refrigerator from the 1950s or 60s? You ever seen, how thick are the walls? Pretty thick. That's because they use the type of insulation, glass wool, like you see in the commercials for attics. And it's pretty thick. Now, when you use a urethane foam, because of the chemistry involved, and it's different, you only need this much insulation. And if you look at your refrigerator in your kitchen now, how thick is from the inner box to the outer wall? Only about this thick, because the urethane foam, this is a rigid one, is much thicker. Let's try something real quick. One of the most useful sites in the whole internet for me personally is this right here. This is the United States Patent and Trade Office site, and allows you access to all the patents online. You can text search back to 1995. You can do title search back to the first patents, 1790. And I usually spend 5 to 10 hours a week, every week on this website. Let's try something real quick. And what I'm doing is a search for any inventor called White in the state of Illinois who's done anything with urethanes. And this is a patent. This allows you rights to either an idea or a molecule or a thing. And up here are the inventors. Anybody look familiar? God, that was a long time ago. Oh, don't look. Anyways, and I did that with Bill Largent, a chemist working with me. I was the lead inventor because it was really my idea. He helped work on it. And it's dealing with making urethane foams. And these are patents, and here I am. So I do know a little about patents, yes, and also urethane foams, yes.
This might be kind of silly, so you brought up refrigerators and how they're made of.
What, hold on.
Refrigerators, how they're made up of the, was it the polyamide or the
Polyurethane.
So in the Indiana Jones movie, when he like puts himself, like locks himself in the refrigerator during the atomic test, like is that actually, like could it withstand that, or is that just?
Well, it has nothing to do with the urethane. It's an area I'm not an expert in because I've never done any nuclear chemistry other than watch the movies about it. But, and that was fiction movie. But I'm assuming somehow they're saying the metal was enough protection. Is it? I have no idea because I'm not a nuclear chemist. It's an area I stayed away from. Unfortunately, I met someone. I was at a party with people who worked at, was it Fermi or Argonne, or I think it was both. And I was introduced to someone later on. I was told her husband died very young. So he was working with very high energetic nuclear particles, and he came up with this very rare lung cancer. And most likely, because of what he was working with, gave him lung cancer, which is, things like that I've stayed clear of. I like living. And some research in chemistry can be dangerous, and also physics. But to answer your question, go to Google and find out, will a refrigerator protect you from a nuclear blast? Well, I guess how far was he from the blast site and what temperature, because metal does melt. All right, now another area, and I'm just going to briefly touch on this, is a phenol formaldehyde polymer. And switch is still off. And this is an area of my last patent, so I know it quite well. You've learned this. If you take phenol, which is acidic, and what was it, the lab I think I'm handing back today, you did this reaction, you'll make the phenoxide anion. And again, this you don't have to write down. And now if you react this with formaldehyde, you have an alcohol condensation. You usually do this in water. So what you'll get after it rearranges is this intermediate. And this intermediate can react with more phenoxide anion that's present. And you get this type of intermediate. Now if you notice, each one of these is phenol, and in the ortho and para positions of each one, I can react it with more formaldehyde and make this polymer that looks like this. Notice we have the different methylene bridges. CH2 is called methylene. And this can further react, get bigger and bigger. And this makes an excellent adhesive. It's used for wood. It's used for many things. The company I work for, the area I work for, that type of big molecule One type is used to keep sand glued together in a shape to make molds that's used in foundries. And because of my position, when there was a problem with our product, sometimes I got called to go to a certain company, and our two biggest customers in this area, and actually the whole company, was GM and Ford. And I had a call one morning from the president of our company, tomorrow you got to be on a plane and go to Saginaw to the GM plant to have a problem with your product line. And the next morning I was in their plant, solved their problem, took a couple of days, but afterward they were happy that I jumped on it quick and solved it for them. And they gave me a tour of the plant. It was huge. The whole foundry was bigger than this campus. People who delivered the mail had scooters inside the plant to get around. It was so huge. And they had these little, about the size, 2/3 the size of this whole desk, from here to here, floor to floor, molds or little railroad cars where they put in the sand, make the mold, it would cure, they'd roll it along mechanically, and they had these big buckets of liquid metal, I'm using the wrong terminology, and pour it into there and cool it off, and they'd get their engines, car engines. And the day I was there, I was watching them make V8 engines for a GM, I forgot which car. And Ford, I saw a similar type thing. And that's a very important polymer. By the way, this type of polymer also holds wood together. And where's one of the funniest places we sold to? It wasn't funny, we made money from it, but the salesman who handled that got a lot of grief and kidding about toilet seats. Have you ever been on a toilet seat that's not solid plastic, and most of them aren't? There's wood, and they use little wood particles, they glue them together, and they use this resin to hold the wood together. So next time you see a toilet seat, you can think that's organic chemistry too. All right, that's everything I can do and you should know about in polymers in 90 minutes or less. All right, guess what time it is? It's new chapter and functional group time. But before I do that, a quick commercial from the management me. Don't forget, a week from today is test number 3. I talked about it yesterday. If you go to Blackboard, announcements, here's the points breakdown, here are the functional groups that it covers. As I mentioned yesterday, best way to study for it is do the practice problems. And like I said yesterday, 7 points general knowledge, 38 nomenclature, 60 reactions, there's 3 or 4 synthesis under reactions. That reminds me, anybody happen to pick up a bottle of vinegar and think about it has acetic acid, which is a carboxylic acid? Or do you happen to do your laundry, use a fabric softener, and that's a quaternary ammonium salt? Or did you use mouthwash and look and see, oh, it's got a quaternary ammonium salt, and that helps keep my hands fresh? All right, new section. And I better warn you, this is an area I worked heavily in too, so I know a lot about it. You'll get some things that most people don't learn about this. Coming attraction in this chapter, I'll teach you the organic chemistry of how soap gets my hands clean and your hands clean, your clothes clean, detergent, and other things you use soap or detergent to clean. And where we start off is talking about lipids, and we'll also later on talk about detergent. So the question is, what's a lipid? And a lipid is a characterization of a group of compounds that are constituents or molecules of plants and animals that are characterized by their solubility properties. Click, switches on for test number 4. And lipids are insoluble in water, but soluble in what we call nonpolar solvents like hexane, ether, gasoline, things that are nonpolar. And these are called lipids. Now, when we talk about lipids, there's two types of lipids. And they're characterized by a certain chemistry. One has, the other doesn't. One type is called saponifiable. And a saponifiable lipid can be hydrolyzed under alkaline conditions to yield the salt of fatty acids, otherwise known as carboxylate anions. What's hydrolyzed under alkaline conditions? Well, that's really a reaction of base and water, saponification of an ester, as you know. And one of the products you get is a carboxylate anion. The other type of lipid is called a non-saponifiable. And hold on 1 second, I thought I got it in here, but I guess I didn't. Notice that little red squiggly line? If I don't shut this off, it's everywhere in my slides. And non-saponifiable lipids when you react them under alkaline conditions, hydrolyze them, you get no reaction. So we have saponifiable lipids that when you react it with sodium hydroxide and water, you get a carboxylate anion. We have non-saponifiable lipids. When you react it with alkaline conditions, or sodium hydroxide and water, you get no reaction. So let's talk first about these saponifiable lipids. Remember my promise to you, no new general reactions. Well, when we talk about saponifiable lipids, what we're really talking about are fats and oils. And what do we mean by fats and oils? Things like bacon grease or fat, vegetable oil, olive oil, things you use in your daily life. So a saponifiable lipid is really a fat and oil, or oil. Now, what is a fat or an oil? Well, it turns out it's a triester glycerol. You might also know it under the name triglyceride. If you go in and have your annual checkup, which I will be due in about a month, the doctor will, my doctor, and I've got a great doctor now, and they'll do a blood test as part of the annual checkup, and he'll check my triglycerides, and if I've been eating too much stuff with fats and oils, he'll tell me that, and they'll also remind me, which he's done, you know, if you have a high triglyceride level, which at one time I did, I don't anymore, he said, you know, you're in the 90% category with your age and that triglyceride to be dead in 5 years. And that got my attention real quick. And he was right. And he's very honest with me, very good, but he'll be straightforward with you, he doesn't beat around the bush. And what is a triglyceride or triester? Now, first of all, I have to talk about oil chemists. Now, people who work in fats and oils, which I am, are called oil chemists. Their society, which is in Champaign-Urbana, is the American Oil Chemists Society, AOCS, and it has nothing to do with oil from the ground that you make into gasoline. We're talking about fats and oils. Now, oil chemists do something a little different than synthetic organic chemists when it comes to esters. As a synthetic organic chemist, I write my esters this way. As an oil chemist, and you'll see this on the internet, I'll write my ester that way. And so I need to show you that because now I'm going to show you the structure, which you should know, of every fat and oil, the general structure. a triglyceride, or fat and oil. And what's the difference between different fats and oils? What's R prime and R double prime? Other than that, they're all the same. And notice, if I use my magic organic chemistry hands and arms, and I go like this, what functional group do we have here? Carbonyl, R group, oxygen, R prime, ester. R group, and by the way, they put their primes here, not here. And here I have carbons, the carbonyl, oxygen, more carbons, ester, second ester. If I go here, carbons, carbonyl, oxygen, carbons, ester. So if we do our math, triester. And it says glycerol, also known as glycerin, that's this alcohol, which we'll talk about. Which you've used as a lubricant in the lab already. And this is a triester or ester glycerin or triglyceride. All fats and oils have that structure. Now, one of the questions you should be asking is, what's the difference between a fat and an oil? Why not just call them all the same? Well, this is the difference. Hint, you should know, which is on full, and that is a fat is a triglyceride that's a solid or semi-solid at room temperature. Again, a fat is a solid or semi-solid at room temperature. I think you all know what a solid is. This is solid. What's a semi-solid? Have you ever had butter on the table for a while? If you take your knife and push it in there, you know how it's real soft? If you really want to do it, you take your finger and push it in there and it's sort of soft, but it's not like to the other people on the table, so you shouldn't do that. But that's what we mean by a semi-solid. Now, that's a fat. What's an oil? An oil is a triglyceride that is a liquid at room temperature. And I think you all know the difference between a liquid, gas, and solid. Hopefully you learned that in general chemistry. An example, the material here in my water bottle, water, is liquid because it has indefinite shape but definite volume. Solid has definite shape, definite volume. And so oil, liquid at room temperature, triglyceride, fat, solid or semi-solid triglyceride at room temperature. You don't need to know it, but if you're wondering, by definition, room temperature is defined as 25 degrees Celsius, which I think is 77, but don't quote me on this Fahrenheit. If you take an oil, I don't know if anybody ever has, like vegetable oil or olive oil, you put it in your refrigerator and come back a day or two later, you'll see a lot of solid in there. Because some of the triglycerides are solid at low temperature, but at room temperature, they're a liquid.
A good example of the oil one is
Olive oil, corn oil, vegetable oil.
yeah, but also Crisco.
Well, Crisco, I think, is this, wait, is Crisco the solid?
Yeah.
So that would be a fat.
It's like
And that's also known as lard, I believe, right? Which I'll teach you the industrial name for those things later on. So if you think about it, I don't buy Crisco, but I remember when I was young, some of my friends' mothers used it a lot, like for frying. If you have it out in the container, can't you stick a knife or your finger in there and it's soft, but it's not a liquid, so that would be a fat. All right, now let's talk about some chemistry. And let's do the following reaction. And better because it says seaboard. If we take this triglyceride, a fat or oil, reacted with acid or water, and probably the acid of choice here would be hydrochloric acid. Why? Because that's what's in your stomach. Now, you look at that and say, what's the answer there? And someone in the back, hopefully, or in the front, or in the middle will say, well, Dr. White, you promised me reactions. And let's take a look at this right here. What functional groups I have? Ester. Now, we're writing it this way. And you learned it where this was switched around. And this is one of the facts of life, how oil chemists do it differently. This is going to give the same thing. Alcohol plus a carboxylic acid, which I'm going to write this way. And I just have my R and R prime switch. It's just like X and Y in a math equation. That's not going to make a difference. Therefore, if we look here, what do we have? Ester. 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 Let's do the top ester. What happens? You get, here's my carbon attached to the oxygen, becomes that alcohol. This part here becomes this carboxylic acid. I don't know R prime yet. Center ester. This carbon, which is bonded to that, do we break carbon-carbon single bonds? No. You're going to have this carbon still bonded to that one, and this one is the oxygen going to the carbonyl, will be an alcohol. So I'll have this alcohol. This will have HO, carbonyl, R prime, will give me this carboxylic acid. And finally, the third ester right here, when you're reacted, this is this carbon here, which will become the alcohol. And this right here, oxygen, will get an H, carbonyl, R triple prime, my carboxylic acid. And this is acid hydrolysis of an ester, but in this case the ester is a fat or oil, which just think of it, and this is now you're learning the strength of functional group chemistry. Just because there's more than one functional group in there doesn't change how it will react. Ester will undergo this reaction. Ester, same thing. Ester, here, same thing. Now, one of the things I think I mentioned the other day, that when I was a student, if something was important, my instructor would tell me, I'd put a star in the left margin. If it was really important, I'd put a couple of stars, 3 or 4. And if it was really, really important, I would do this. And you should too. And the question is, why is this really, really important? Because this is how your stomach breaks down fats and oils. If you consumed anything with fats or oils in it, and breakfast today, if you buttered your toast, the butter has fats and oils, mainly fat. They're in your stomach. This reaction is going on. By the way, there's chemistry going on here, organic chemistry, all the time. And what you're making is glycerin and fatty acids, which your body uses to do various things. And now well beyond my level of expertise of how should I say, it's biology of the body. I guess they teach that in they teach that in microbiology, or they teach that in A&P. I hope they teach you somewhere around. But anyways, you should know this reaction because this is how your body breaks down fats and oils. And the only difference between different fats and oils are what our prime and our double prime are. I'll talk about that in a little while. Excuse me. Oh, time flies when you're having fun with polymers and fats and oils. Now, the other reaction, which I showed you with an ester, is base hydrolysis of an ester. And again, what do you get? Ester, I'm just writing it backwards. You get back the alcohol you would have used to make that ester, and then you don't get the carboxylic acid because in the presence of base, you get the carboxylate anion. And you just learned it reversed around the order of what you get, but we went through this already. So if I look at this first ester, here's my R group on the oxygen. Here's my carbonyl, here's R prime, using this example, even though it's called R. So my R group here is CH2, that alcohol. My carboxylate anion will be this right here. My next ester, here's my RCH, but you don't break carbon-carbon single bonds. So this will be this alcohol. Then my carboxylate anion, O minus carbonyl R prime. And finally, my last ester, my triglyceride, my fat or oil. Here's my R group, CH2, but you don't break carbon-carbon single bonds. And you get this hydroxyl group or alcohol, interconnect together, you get glycerin. And the last carboxylate anion is this one. And you get this. How many of you have ever seen someone or tried it yourself, made your own soap? Nobody? But, oh, one person. How did your ancestors long ago make soap? They boiled up fat or oil, usually animal fat, with some water and some lye. Now, lye is the old common name for sodium hydroxide. And what they were doing, and if you remember I used the term, this is called saponification of an ester, because these carboxylate anions from fatty acids, we also have another name for, and that's soap. And that's how this got the name saponification. And your ancestors, years and decades and eons ago, made soap in a big kettle by boiling fat with lye and water, sodium hydroxide. And they made soap that way, and we'll learn more about soap. I work for a company that made these carboxylic acids and also the carboxylate anions. I think I might have mentioned it. You can press them together, the carboxylate anions, just like your bar soap is a solid at room temperature. And they make pellets this big, and somehow in the soap industry, those are called soap noodles. Not that I would ever eat one, but they're called soap noodles. And with that, I'm going to let you out a whole 25 seconds early. Those of you who have, first of all, everybody who celebrates it, I hope you have a happy Easter. You get all the chocolate bunnies you desire. And for those of you who don't, I hope you have a happy holidays.